Okay, I'm just going to go through a little bit of electricity. The first part of two. It's not really two halves. Electricity is the harder elements of electricity, and the second part, really, EMF, internal resistance, and potential dividers tend to be the main issues. But I've got to go through this part, and if people want to, I will I'll make a second part as well. Okay, just really to help new teachers, if it's a new topic really for them. Okay, so this PowerPoint, by the way, is just a free PowerPoint, freely available on the internet. I've tried to use things that are freely available, really, okay, not proprietary stuff. So first, there's a first slide here about charge carriers. Really, we're only going to be looking at electrons, really, in A-level physics, but there's a whole gamut of other things there on this screen that you could talk about. More chemistry, really, than anything else, or maybe electronics in some cases, but yeah, so conduction electrons isn't really what we're going to be talking about that are carrying the charge, and generally of metals. Good conductors have got, lots of free charge carriers, and insulators have few, so that's something they should be aware of already. Immediately here, there's a bullet point which maybe would be better later on, really, in this presentation, talking about sort of special case of the temperature of semiconductors like silicon when they're increased. More charge carriers being produced, and so the semiconductor turns from an insulator into a conductor. Now, really, we're talking about thermistors, really, here, so that's where that comes into importance later on in the PowerPoint, really. We've got a PowerPoint slide here about conventional current flow. Again, this isn't a massive deal, really, at the start of the electricity, really, because the idea or the understanding that electrons flow really from negative to positive terminal, it only really becomes important when we look at magnetic fields and a beam of charges, making sure that you use FBI correctly, okay, if you use that rule, Fleming's rule. So it's worth mentioning at this point, and there is a really good video listed at the bottom there, a TED video, which is really good. You can watch this with GCSE or A-level students. It talks about the language we use from the word like electricity and electrons and things like that. Gives you a historical perspective, looking from ancient times to Gilbert and to Franklin and things like that. It's a really good sets of scene anyway. Okay, so whilst it's worth mentioning, it's not really going to figure in anything that we're doing really in this topic. First equation that generally is covered at A-level is something that's covered at GCSE again. So current being the rate of flow of charge. So by definition there, I equals delta Q over delta T. Don't need the delta symbols when you're working out calculations or anything. It's worth stressing. Worth mentioning that amps is fine. Coulombs is a unit that often students struggle with at GCSE and at A-level. I think they kind of forget about that unit and they confuse charge and current quite easily. Worth emphasizing what rate means divided by time, because it comes up throughout physics, and always worth emphasizing that. But there should be a familiar equation to them, quit or Q equals IT, or that's the better way really, the first way, I equals delta Q over delta T. To introduce the concept of current. Then a little bit about energy. You've got to be careful with energy that you don't cause problems by contradicting things that students are taught at GCSE about energy stores. At this moment in time, a lot of resources are still talking about energy transfers as opposed to energy stores at A-level, and this is one of those ones. Okay, so the battery gives the electron a fixed amount of energy. Talking about chemical energy transformed into electrical potential energy originally, and work done has got to be done passing the electrons through devices, and the main device they're going to encounter initially is the bulb. Causes the electrons to lose their potential energy or some of it, and the bulb emits heat and light. So yeah, just beware if you want to stick with the stores terminology or not at A-level. Either side of the bulb there exists a difference in the electrical potential, so that's where potential difference comes from then, and that's a nice way of introducing it, potential difference or voltage. And there's a schematic there down below, the electrons going back to the battery and so on. It's worth stressing all throughout this topic that everything's based on models. In reality, electricity is a very complicated topic, and there are loads of different models that we use at various levels of education. The Drude model being, I guess, the main one at this kind of school level. And we use lots of different sort of simple models in class. I've got one of those ones of the penguins going up a sort of mechanical staircase and things like that, just to try and get the idea of the energy being given to the electrons and things like that. Whatever really helps the students understand what's going on from what they can see. This is another model here. This is from a Keith Gibbs resource, I think. I thought it was quite helpful. Again, it's just a model, and you have to emphasize that if you're looking at drops in potential through a circuit there, you've got obviously the large resistor is going to have the larger potential drop. And I think some students have found that quite helpful over the years to get an understanding about what's going on. So definition there, potential difference. So the work done per unit charge passing through a device. That per unit charge or per unit coulomb, is something that students often struggle with. I struggle to say it then, for instance. But yeah, it's always worth emphasizing this early doors about this work done per unit charge or per coulomb. This is an equation, again, that they should have covered at GCSE, depending on which course they did. From here, you could see that voltage is equivalent to, well, a volt is equivalent to a joule per coulomb, which could be useful often in multiple choice questions when you have to work on units and in terms of sort of checking students can change units around and either simplify something as base SI units or just an equivalence. That relationship there is quite useful, 1 volt being 1 joule per coulomb. So then we can use both of these equations, rearrange them, stick them together, and you can get energy equals IVT. Whoops, I prefer energy equals IVT than work done, to be honest. I'm not a big fan of the capital W, really, but there we go. It's what's in the textbooks. So energy equals IVT, which again, when the course that we teach at XLI GCSE, then that's in there as well. So that's not unfamiliar to students. And then we lead on then to power, P equals IV, by considering power equals energy over time and substituting in and cancelling the T's, or the delta T's in this case. So again, that's an equation that students should be familiar with. I think that's probably in every GCSE course, really. Now, resistance is where it starts to get a bit more cognitively challenging. I think at this point, I just sort of talk about resistance. I often put on the board 2 sideways views of wires, one wire at room temperature, one wire at higher temperature, and then show the vibrations of the ions and then some electrons coming from left to right. And we talk about the interactions between the electrons and the ions, trying to get across that the ions vibrate more at higher temperature, and so the resistance increases, that kind of thing. But resistance then, the definition being voltage across a component divided by current through it, measured in ohms. Sometimes students struggle with the symbol for ohms. It's not something they always see that often because it's usually written in letters. The other units should be fine. And so yeah, the text below there is not a definition at all, but sometimes it can be useful for students to sort of think this way, that resistance is a measure of the difficulty of making a current pass through a substance, caused by the repeated interactions between the charge carriers and the ions of the substance. And we could talk about long wires and short wires and thick wires and thin wires as well at this stage. I don't think it's in this particular PowerPoint, but that's a good thing to bring up either now or after you've done resistivity. And in terms of measuring resistance, come across this very basic circuit now, which, again, everything in the circuit should be familiar to students who've done GCSE. Worth emphasising the positions of the ammeter and the voltmeter in case students were uncertain about that. And also the reason why there's a variable resistor there. And the resistor there, the fixed resistor, could be any component, worth emphasising that as well. Then just a list of instructions that you'd normally expect to see in a GCSE kind of answer, long answer to how you'd investigate the IV characteristics of a component. Nothing really there new. The only thing there to emphasize probably would be about the resistance of the voltmeter being infinite assumed and the ammeter having zero resistance being the other assumption. There was a recent question with the AQA. I think it was a voltmeter that wasn't ideal, and so that was a bit complicated, but worth maybe mentioning at this stage, or certainly when you're revising, that we assume the ideal nature of these things, but you could have a question where they're not ideal, and then you'd have to think that through. Ohm's law, really important to cover as well. Obviously, the definition given there, voltage across a conductor proportional to the current through it, provided the physical conditions are constants, and temperature is usually fine to write down there as the physical condition. One thing that I do try and emphasize is this thing at the bottom, particularly for my exam board that a device to be ohmic, the resistance has got to be constant, because quite often that's not the natural thing that students come up with. So definitely worth pushing that. So a VI graph or an IV graph would be a straight line because the resistance is constant. Some weaker students might write that the definition of something being ohmic would be that it obeys Ohm's law, but they're repeating the question there really, and it's worth, even at this early stage, pushing the kind of thing that's expected from them in an exam. So there's a straight line graph. There's no other information, I don't think, on that slide really, particularly. Now everyone's got a different way of doing things. I don't really like the solidus there, or the slash. I always prefer putting units in brackets myself, because I think it looks a bit messy, especially when you've got logarithmic functions later on in the course. But worth talking about that again, about units as well as variables on the axes. And also, it might be worth pointing out, quite often it's milliamps on a current axis, and taking that into account then when you do any calculations based on the graph. In this case, the gradient is going to be the resistance. But again, it could have been an IV graph in which the gradient would have been 1 over the resistance. Resistivity kind of follows naturally on then, okay, a property sort of a material as opposed to a property of an object. It's got the symbol rho. You've got to be careful there about rho being the symbol for density as well. And I have seen at least one question in the past where they talked about resistivity and density in the same question. So the next few slides are just talking about how this situation is built up, that resistance is proportional to the length. It's kind of what I was referring to earlier. Inversely proportional to the cross-sectional area. You can talk again with some models about why these things are the case. And then we build up this picture of this constant in this particular equation. Resistivity being RA over L. Quite often, it's quite often the case that students are confused with this equation, and when they're working through questions, they sometimes put the resistivity in as R and things like that. So worth emphasizing some of the pitfalls there of using this equation. Sometimes they just confuse the subject of the equation or the relationship between the variables. So always worth checking the formula booklet. And the unit is sometimes given a free mark in the exam. At the end of the question, they'd say with a suitable unit. Similarly, you get those questions about to a certain number of significant figures, and it's worth writing, sort of mentioning to them that when they read those kind of things at the end of questions, to circle them or highlight them in some way, so that when they've done the numerical calculation, they might notice that they've already highlighted something, and to stop for a second and then consider what else they need to write to get the full marks. Otherwise, it's an easy mark lost either for the unit or for the significant figures. So as I think I mentioned this earlier, resistance being a property of an object and resistivity being a property of the material. This is something I revisit again towards the end of year one, once you've done materials as well. So you've got things like Young's modulus, breaking the stress, and resistivity all being properties of a material, as opposed to something like resistance, which can change depending on the geometry of the object. You've got some values here. I always stress that you don't have to memorize them at all, but almost every question is going to be about a metal or a metal alloy, and so you're going to be looking at something like 10 to the minus 7, 10 to the minus 8, 10 to the minus 9, maybe for the resistivity. And there's some other materials there which are not really likely to come across, at least not in my experience, really. But ballpark figures are always useful. Then we come on to superconductivity, which they can only really ask questions really that are qualitative really in this particular topic, certainly with our exam board, AQA. So a state where certain materials have got zero resistivity occurs at or below the critical temperature, sometimes termed the transition temperature, depending on the course, or the era of the course sometimes, which depends on the material. So the critical temperature would be well below minus 200 degrees generally for lots of materials. Some courses, I might think in sort of class things as high temperature superconductors and low temperature superconductors, but when we say high temperature, we're still on about very, very cold. It's all relative really, okay? Applications then might include very strong electromagnets. You could have a bit of a segue here and talk about the Meissner effect and magnetic fields if you want. There's an opportunity there, but obviously that's beyond the course, or most courses, I would imagine. You could talk about power cables, efficiencies in substations and things like that, and preventing heating of substations. You could talk about supplying huge projects that are power hungry, like the Large Hadron Collider, for instance. Then we've got a graph then of resistivity against temperature. This line, the line going downwards, most exam boards will accept either a straight line there or a curve, and then a shooting down at the transition or critical temperature. Okay, and then it being zero all the way back to the origin. You've got to be careful about the axes sometimes, just whether it's degrees Celsius or Kelvin, but not really anything that's going to come up, I don't think. This is a page from a revision guide, so you've got some further uses there that you can talk about. So they call it transition temperature here. Like I said, you've got to be very careful. I contacted our exam board really recently talking about some older exam papers wanted a certain thing. I can't remember if it's transition or critical, and then they seem to swap what they wanted then in more recent papers. So always check the exam board. There's some other uses down there as well, fast circuits and things like that. Nothing major there, I don't think. The components need to all be sort of understood, some more than others. The ones on the left certainly are going to be really important, and some of the ones on the right as well. The heater and the electric motor, they tend to mention that it's a heater in a question, but the motor I haven't seen come up that often really, and again, they probably tell the students that was the case. Now, thermistor symbol is a bit controversial. I think that's the wrong way around, that arm there on the thermistor, on that particular graphic there. I think it's righted later on in the PowerPoint, I think. But they need to be familiar with these, and sometimes there's circles around some of these things, like the light-dependent resistor. I always make a point about indicator. Both exam boards we do for IGCSE and A-level talk about an indicator as opposed to a bulb, and I've never really agreed with that, because you can have current flowing through a bulb and it's still not light up, so it's not necessarily an indicator of whether there's current flowing at all, really. And so I've always had a bit of a gripe about that, but that's just me, I think. Worth indicating about the arrow there, indicating which on the LED or the diode, indicating which direction the current needs to flow for it to work or to allow current to pass. A little bit here then about notes on those components. So a cell, and then being a series of cells being a battery. There's a nice little bit back in that TED video about batteries and where the word came from. Historically, I think it was about ships and batteries of cannons and things like that. And there's a bit about the indicator there. Not the world's best definition, or right up there about what a resistor is. Yeah, and thermistors, it's worth emphasizing that thermistors, the resistance goes down with increasing temperature, which is contrary to pretty much most things that the students will encounter. At GCSE and A-level, I often use the acronyms or the phrases TERD and LERD. So TERD for a thermistor, temperature up, resistance down, and LERD for a light-dependent resistor, light up, resistance down. They're quite memorable, those acronyms. Okay. We'll talk about how that works later on. And there's the LDR again, so the resistance goes down as the light goes up. Diodes allowing current to flow in one direction, the forward direction. Now, diodes at A-level, even A-level, is very simplistically treated. So we say in the negative, in the reverse bias direction, they don't have a current, we say, and it's up to you how deep you go into that, really, but often I do show a proper graph which shows a breakdown voltage in the reverse and a very small dark current, but I don't know, sometimes it can sort of confuse students, whether what they need to know for the exam and what actually happens in real life. Okay. Now, LED, there's nothing really else there on that slide. So then we move on to the IV curves, and it's always worth asking students where they think the negative values come from, for instance, in these graphs. They do quite often have to know both IV curves and VI curves. Now, go back here now to that basic circuit there, the variable resistor way of doing things. It's worth at this stage talking about a more sophisticated setup, the potential divider control, even though they wouldn't have come across what a potential divider is. I do talk about this quite a bit at this stage. And then that YouTube video down there, it's very short, but it really succinctly gets to the point about the difference between these two setups. The circuit on the left alters the current, and the circuit on the right alters the voltage. The circuit on the right is the only one that will allow you to go down to 0 volts and up to maximum brightness. So the range of voltages is much more superior on the right-hand circuit. Ultimately, though, in exam papers, I've seen it in at least one long answer question that there was an optional mark was for mentioning that circuit on the right. So it isn't normally a deal breaker in questions, I wouldn't have said. Most students can get away with just talking about the circuit on the left for lots of questions anyway, as it says there. So it's less complicated, the circuit on the left, but you're restricted a little bit in the values that you can get. And this, I think, this is taken from the Adams and Allday book. It goes into a bit more detail about both circuits. Talk about rheostats then as well, because the video, that little YouTube video, has got a section about using the rheostat in it. Well, they've got a rheostat in the circuit connected with 2 connections and then with 3. And at this stage, it's worth really showing the students how this works. It's the 3-stage connection, because it's not always obvious the first time you do it. So it's worth taking a variable resistor like this in your hand and explaining exactly what's going on at this stage, I would say. Then we're on to the IV curves. So I've got both VI curves and IV curves. I mean, it's not massively important for a wire or a fixed resistor because a straight line is a straight line. But again, you've got to emphasize that the gradient of the VI line is going to be equal to the resistance, but 1 over the gradient is the resistance for an IV line. Okay. So filament lamp, again, you've got this reflection in the x equals y there between both graphs. And this is the one really that they need to sort of nail their understanding, because it comes up quite often, particularly multiple choice questions, where they, and sometimes in long answer questions, they might have to draw or sketch a specified graph, whether it's IV or VI, and they have to get the orientation correct. Okay. And they also have to be able to explain why the resistance of the metal increases as the temperature increases and so on, and explain what's going on with the curvature of the graphs. So that's something you need to spend quite a bit of time on usually. And all of these components is worth doing investigations in class of these. It can be quite difficult to do the filament lamp one correctly, but maybe I'll do another video on that about how we can do that properly, because with a poor choice of components, you can sometimes get a misleading result in terms of the graph. It can sometimes look like a straight line, for instance. So it doesn't obey Ohm's law, and that's worth emphasizing. If you have to find out resistance at a given voltage and current, remember never to say drawing a tangent or anything like that, okay? Because often with other curves, you might draw tangents, but certainly not with this one, okay? So you're finding a resistance at a given voltage and current, so you just take a pair of coordinates. So a bit about the thermistor here. Again, we're repeating ourselves there with the resistance going down with increasing temperature. The IV or VI curve or line I don't really see come up that often. It's more really the consideration about the resistance temperature graph, okay? That comes up in our IGCSE course, but you can see there that's the proper symbol there for the thermistor. And worth mentioning about the 2 different types, that most thermistors, and pretty much every thermistor I've seen in an exam question, be a negative temperature coefficient, but there are positive temperature coefficient thermistors too. Then LDRs, light-dependent resistors, worth mentioning that you should never really write the abbreviation down in the exam. Certainly the first time they write it, they should write it out in full. A bit like TIR when you do waves, it needs to be written down in full to get the marks. So you've got bright and dim LDR situations there, and you can see the difference in the IV lines. Again, the most important thing really, I think, for LDRs would be the curve on the next page then. Which has just been taken from a GCSE guide, okay? So yeah, they've got very similar shapes there, okay? And turd and lurd for the win, I think, on that. A little bit about the diode here. So this one, I always find the VI curve to be a little bit non-intuitive. I'm not really sure why. Again, it's just the same kind of reflection. But more often than not, you see an IV graph for diodes. And the knee or turn on or switch on voltage used to be a given that it was 0.6, but most of the time these days they say in the question what the voltage is, the switch on or knee or turn on voltage, in modern questions anyway. Worth talking about the reverse direction there being 0 in the exam, but probably a dark current flowing. Yeah, depends how much detail you want to go into really there before you go into electronics too deeply. Oh yeah, worth adding. But the thing about the if you're using a variable resistor, worth adding a safety resistor in series with the diode, because that's usually worth a mark in a long answer question. Now this bit, I nearly would have removed this, but I've seen some recent questions in the AQA board that actually ask for this kind of information. So if you have a combination of components, in this case a diode and a resistor, then you might get this kind of hybrid line or graph. Okay, and like I said, you could remove it, you might think, but then fairly recently they did ask a question. This one here, look, you could rule out most of the answers pretty swiftly about which possibility would be the case here, but I was quite surprised when I saw this come up in an exam, in a modern exam anyway. But it's worth, again, it's an opportunity to go through the question and rule out the others and work on exam technique really there. And there's a variable power supply, DC power supply, which you don't often see the symbol for either in that question. So a little bit here, then at the end, maybe it's a bit out of sequence really about resistance and temperature. So metallic conductors, then the resistance increases slowly with temperature. They're PTC, and then going back to that kind of idea or model of the ions vibrating more at increased temperature. And you know that's a bit of a loop back to fairly early in the PowerPoint, and then talking about NTC thermistors and how they work there. Okay. Students are often interested in how they work, but it's a very fine line between sort of telling them a little bit of information and then going heavily into the electronics of it, because it isn't that trivial, as we all know. But I often say that there will still be the same effect of the ions vibrating more, but then it's swamped by the increase in presence of charge carriers, and that will swamp that effect. That's normally enough to satisfy the students' curiosity. Okay, and that's the end of that. I've made some videos on YouTube about how you can use thermistors and LDRs in the circuit. You might want to have a look at those if you're interested, about sort of night security lighting and things like that, and temperature sensors. But that's it for this video. But I hope you've enjoyed it. If you want, let me know if you want me to make another one on the more sort of complicated aspects of electricity. But this is just a trial run, really. Okay, thank you very much.